Okay, Year 12, welcome to your video on IEEE754 or single precision, or the way in which computers handle very large and very small numbers. Okay, this is what you have to be able to do. Convert between decimal fractions and the equivalent IEEE754 floating point representation. This is what we are going to have a look at. This possibly doesn't make any sense to you just yet. Don't worry, but know this is what you have to be able to do. It's the conversion. That's what they will test in the HSC. Okay, fractions in binary. We know binary is base 2, so you're familiar with a lot of this stuff in here, okay? So we know we start with 2 to the power of 0, 1, and 2 to the power of 1, then 2 to the power of 2, then 2 to the power of 3, then 2 to the power of 4, and we stop at this point if we want 8 bits or a byte, but essentially we could keep on going and get up to 16 or 32 or 64 in a row, okay? We know that by each time we increase by 1 bit, our power increases by 1. So we start at 0 and then we go 1, 2, 3, 4, 5, 6, 7, 8. That's how we get these numbers underneath. We increase the power by 1. That's for positive numbers. The same goes for decimals. So here's my decimal point, except this time it's a negative. And as I keep on moving away from my decimal point, my negative increases. So it's 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and so on and so forth. That's how I get these numbers down here. Okay. So how do we represent these numbers in base 2? Well, if I have 0.5 in base 2, that's this here, okay, that would just be 0.1. If I have 3.75, so I've got the 3 element to deal with, I've got these two sections here. 3 is going to be, well, it's made up of 1, 2, 3. Yep, excellent. 0.75, okay, that's 0.5, and then I got plus 2. Yep, there we go. Okay, so to represent 3.75 in binary, it's 11.11. Okay, now we're not doing whole bytes, obviously, because we're just doing small numbers. 17.125. Okay, let's have a look at this. How can we make it up? Well, we're going to go... Okay, well, I know just from having a quick look at these numbers just here from the top of my head, I know I'm probably going to have to use 16 because 8 plus 4 is 12, 13, 14, 15. There's no point in doing that. So I'll start at 16 and I'll go 0, 0, 0, 1. Okay, so that's 17. That clears my whole number there. Then I need to get 1.125. Oh, hold on, look, there it is down there. Okay, so I can just go 0.001. Okay, so that's 17.125 in binary. Cool, okay. What about this one? 0.1. 0.1. Oh, that's 0.5. That's 0.25. That's 125. If I did 2 to the power of negative 4, I get 0.0625. Okay, that's not going to work. I used a converter. I cheated. I'll give you a hint. 0.1 in binary is going to be this. This would take you a century to work out. Hold up. I'm just going to delete all of this. Whoa, too much. Go back. Okay, I'll do it in blue then. This is 0.01 because it's not made up nicely of any of these, and trust me, it's not made up nicely of any of the others. 0.0001100. 110011001110. Right. And that conversion, this giant ugly number in itself is kind of rounded, because if we actually convert it back to decimal, we get 0.9999990462356. Oh my gosh, what the hell? Here's what I wanted you to take from that weird long last example. Conversions from binary to decimal and vice versa aren't this easy. And if I'm storing something like that, geez, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's going to take up a lot of memory. Okay, and that's just one number. Imagine like 0.0001248. Like, that's going to be an absolute nightmare. So what do we do? Well, some very smart people a little while back kind of sat down and had a look and said, well, in the real world in decimal, big and small numbers are represented using scientific notation, and everything is represented as 2.5 times 10 to the something. Okay, that's how scientific notation works. So why can't we see if we can use something similar to that? The IEEE, or Institute for Electronics and Electrical and Electronic Engineers, recognise the need for a system like scientific notation to represent really big and small numbers. And this is the system they came up with. They came up with IEEE754 Single Precision Floating Point Representation. It's a big giant name for saying, let's make our life a little bit easier. IEEE 754 in any instance uses 32 bits to store the data. A minimum of 32 bits to store any decimal number. And let's just have a look and see how they actually do it. Okay, I've put a little table up the top here. It has 32 boxes along to represent our 32 bits that make up our IEEE 754 single floating point representation. The S in the first box symbols, it stands for the sign. If it has a 0 at the front of the 32-bit point, it will be a positive. If it has a 1, it will be a negative. Okay? These boxes here, these 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, okay, they make up the exponent. The power of 2, you will be multiplying the mantissa by. But it's a little bit complicated. It's stored as a value in excess of 127. So whenever you get the answer, so you put that convert the ones and zeros from binary into its decimal equivalent, you have to subtract 127 from your answer, and then this is the fractional component of the mantissa. Okay, now if you don't know what a mantissa is, look it up. Don't worry, it's going to make sense in 2 seconds' time though. Okay, let's have a look at this example here. This is an example of a IEEE 754 floating point representation number. Okay, I've started with a 1. Okay, so my S over there, sorry, I can't really point, my toolbar's in the way. My S over there is a 1, so I know it is going to be a negative number. So I'm going to introduce that already. S, it's going to be a negative. Okay, my E component, and this is just how I represent it. My E component stands for my exponent, and that's going to be 1, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, yep, that's that. And if I work out what that, I'll convert that binary to decimal, so if I can put these underneath it. I'm hoping by this time in the term, guys, some of you are getting pretty close to being able to see what that number was. So that's 1, 2, 3, 31. Okay, so that there is 31. So my E is 131. 131 there. And now remember, I have to do it minus 127. So 131 minus 127 equals 4. Okay. And finally, we have to deal with the fractional part. So this is the part past the decimal point, this stuff in here, okay? And that is going to be start not at 1, 2, 4, 8, 16, 32, 64, blah, 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 blah. We're actually going to start the reverse way, okay? So a reminder, we had a look at that in one of the first slides, but if I've got 1, 1, these are just whole lots of zeros, so I can almost really kind of ignore those for the moment. This is my first spot of the fraction, so the first spot after the decimal point. So that's going to be 1 times 2 to the negative 1. Okay, and this is my second dot point, my second point after, so that's going to be 1 times 2 to the negative 2. A reminder, the further I move away from the decimal point, these negative powers increase. Okay, so 1 times 2 to the negative 1 is 0.5. 1 times 2 to the negative 2 is 0.25, so that's going to come out as 0.75. Okay, it's going to sit at 0.75. So this big long IEEE 754 number converted looks like this. Here we're coming in for the win. Negative 2 to the power of 4. I got the negative because it was from there, times 1.75. That's what that looks like. negative 2 to the power of 4 times 1.75. Okay, and if we keep on working on with this, because this is our last step, now we need to just break this down. Negative 2 to the power of 4 of 4 is negative 16 times 1.75 is going to give me negative 28. And that's it, guys. That's what you have to be able to do. You have to be able to get to this point. So first do this, then do this, then do the last point. That's the transition. This is our last example. I haven't included it within a table, so you can hopefully see if you can work it out without the kind of fancy tables. I know that the first thing is my sign. So that's going to be, it's a 0, so it's going to be a positive number. Okay, I know that this section here is my my exponent, and minus 127, so it's going to be, this is going to be, oh, and hopefully I don't have to write the 128, 64, 32. I know that that's 1, that's 2. Okay, so that's 3 is going to be 3. 3 minus 127 is going to give me, oh, and I should do equal signs under equal signs, shouldn't I? Is going to give me minus 124. Okay, and then I'm going to deal with all of this. Like before, because these are all zeros, I kind of don't have to worry about them. I've got 2 to the power of negative 1, so my fractional part of my mantissa is going to be 1 times 2 to the negative 1, whoops, plus 1 times 2. Now I skip negative 2, so I don't need to do that. That basically becomes nothing, and then it's 1 times 2 to the negative 3. Okay, so 2 to the negative 3 is sitting in there. 2 to the negative 2 didn't have anything, so that's okay. 2 to the negative 1, I know off by heart from last time, is 0.5. If I typed in 2 to the negative 3 in my calculator, I would get 0.125. 0.5 plus, plus 0.125 is going to give me 0.625. And then if I write this out nicely, this is what I'm going to come out with. I'm going to come out with equals. It is a positive number, so I can put a plus in there if I want to kind of know what it is that I'm doing. 2 to the power of what? 2 to the power of negative 124 times 1.625. This 1 just means times it by everything here. That's what we're trying to say. Now, this number has heaps of zeros. If you actually go and plug this guy into your calculator, it'll be oh, sorry, I wrote 14. That's meant to say 124. I apologize, guys. Now, this number, if you go and put it into your calculator, is real freaking ugly. So the HSC questions will always specify, but don't worry. Do not worry about actually writing out the thousands of zeros, like actually getting the answer. The last example that we did had a really nice answer. This one doesn't. The HSC questions will always specify, however.